Okay, this is EET112 Lab2, and I was going to show you the scope measurements for measuring the capacitor value. So this is we're going to try to measure the 10 nanofarad capacitor. And so the first thing you're asked to do is program the function generator for 2 kilohertz, 10 volt peak-to-peak sine wave. Okay, so I've done that. I've programmed my function generator, 2 kilohertz, 10 volt peak-to-peak. And now I'm going to probe the output of the function generator. So I'm probing the red and the black clip leads from the function generator cable with probe going into channel 1. So the first thing I'm going to do is hit default on the scope. That's the little light green button. Puts the scope back to its default state, so I know it's not programmed in a strange way. And then I'm going to turn on the output just above the BNC cable on the function generator. It says output. The light turns green, and you can see the slight rising edge on the scope. So obviously I'm seeing part of a cycle of the sine wave, so I need to turn the horizontal to a higher number of seconds per division. So there you can see roughly 2.5 cycles. I'm clipping, so I need to turn the vertical amplifier gain down a notch to 2 volts per division. And then I'm going to hit the measure button here to get the peak-to-peak rating or measurement. So it's measuring about 10.32 volts peak-to-peak, but I'm not averaging the signal, so I am included with that measurement is some noise that's riding on the signal. So if I hit the acquire button and then the acquisition, I'm going to put it on average, and I'm going to go to 32 averages and then select it. And let's see what it settles out to. So it looks like 10.08 roughly. So that's pretty close. I think I'm just going to stick with that. And now I'm going to, I breadboarded my circuit as you see in the photo in the lab doc. So I got the 10K resistor in series with the 10 nanofarad capacitor. And now I'm going to probe the voltage across the capacitor. But I'm going to leave the function generator. I'm going to connect the red lead of the function generator to the opposite side of the resistor, like you see in the photo there. So I'm going to turn off the function generator output, and I'm going to hook that up. So let me do that. So now I'm going to probe the output of the cap, and I'm going to turn the generator back on, and I'm going to clear sweeps here to restart the averaging. Actually, that didn't. I'm just going to toggle the horizontal back and forth. I know that restarts the averaging. And you can see we're settling out to maybe 6.08 volts peak to peak. Now I'm going to turn averaging off because I'm going to make some fine adjustments on the function generator. So back to normal, select it. And now I'm going to, we need to adjust the function generator amplitude so that we get 5 volts peak to peak reading on the scope. Okay, so it looks like I can turn the scope gain up a little bit. I'm still not clipping, so I do that to get more accuracy. And now I'm measuring 6.04. So I need to turn, if you look at that plot in the lab document, you see that we'll need to turn the frequency up. We're at 2 kilohertz now. We're going to have to go up to near 2.4 was our theoretical frequency, to which we'll get 5 volts peak to peak. So I'm going to hit the frequency, and I'm going to put the cursor on the function generator in the tenths of a kilohertz column, and then I'm going to use the knob, the round knob, to adjust it upwards. Okay, so we need to get to 5 volts. So here's 2.1 kilohertz. It's dropped it down to 5.8-ish. So I'm going to go right to 2.4. So I made that adjustment, and we're at 5.4. So I need to go higher. I'm going to go to 2.5, 5.28, and then I'm going to go to 2.6, 5.12. So that's pretty close, right? So now let's turn on averaging and see if it settles down to something close to 5. So turn the averaging back on and select it, and let's see what it settles out to. 5.04. Pretty close. Maybe I could make a super fine adjustment, but if you get that close, I think you should be happy. I'm going to move the cursor of the function generator over to the hundredths column, and I'm going to just go up a couple tenths and let it settle out here. Remember, I've got 32 averages, so it's going to take a little time to settle out. It's at 5.04. I go up a couple more. Here's 2.64 kilohertz. Looks like it's not moving. So we may be within the resolution of the scope, like 0.04 volts. Maybe the next measurement, it's going to pop down to 5.0. I'm going to try one more tenth or hundredth of a kilohertz. There's 2.65. Still didn't move it. All right. There's 2.67. So 2.67, it looks like it dropped it to 5.00. You know, I'm not going to get any closer than that, obviously. So for my particular circuit, my 10K resistor, which let's say I measured it at 9.9K, for example. Now I'm going to use that value in that equation, square root of 3 divided by 2 pi f times r, where r is your measured 10K plus the 50 ohms. So I'm going to use that 2.67. And let me just calculate that really quick in case you're interested. If you don't want to wait for the calculation, that's pretty much it for the video. So square root of 3 divided by 2 pi f r, where r is my 10K resistor plus the 50 ohms. All right, let me calculate that. Find my calculator. Where'd it go? There it is. Okay. So 3 square root 2 divide pi divide the frequency I was 2.67K. 2.67K divide, and then I had 9.9K was my measured resistor value. 50 added to that, divide, and then put it into engineering notation here. So I calculate 10.376 nanofarads for my capacitor using that equation. Hopefully you get something close to 10 nanofarads. If you're using one of those weigh-in top caps from the weigh-in top kit, those things are not very, I mean, their tolerance is all over the map, so you may not measure something close to 10. If you have the DMM, the Astro AI DMM, it also has a capacitor measurement mode, so you could check your value with that and see if that matches up with this scope measurement. All right, let me know if you have any questions.